Hello friends, in this video we're going to discuss about semi-empirical mass formula. This is the formula. So this is binding energy equal to this, right? So we're going to explain, we're going to discuss each and every term here. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. If you want to follow me on Insta, this is my Insta ID OJHALAKHYAJIT123. This is my Insta ID. You can follow me on Insta. Okay, so now let's start. So here is the formula. Binding energy for the nucleus is given as this. So here this is the number of protons and this is the mass number A, right? So here you see, first let us explain this term, then we're going to explain this, then this one, then this one, and then one by one I will explain all the terms. Okay, so let us discuss about the first term. Before that, let me show you this graph. This graph represents here it is here you see the contribution of each term that involved in this formula. Their contributions are shown here, right? Relative contributions of various effects in the semi-empirical formula are shown here, and here you see this is nothing but binding energy per nucleon versus mass number graph, right? So here is the graph. Okay, so this part above this graph, binding energy graph, this is asymmetry energy, and this as this line, this bottom line is the net binding energy per nucleon, and this portion is surface energy, right? And this portion is Coulomb energy. Here you can see this portion, right? So this is the graph. Now let me explain the first term. So that is first term is volume energy term. Let me write BV here, so which is equal to AV capital A. This is the first term, this one, right? So here you see, the volume effect representing the volume energy of all the nucleons. Larger the total number of nucleons, larger the number A, the more difficult it is to remove an individual nucleon from the nucleus, since the nuclear density is nearly constant. So now you see, larger the number mass number, so it is difficult to remove an nucleon from its nucleus. So that's what it is explained here, you see. Now this volume energy, now the nuclear mass, first let me explain this. Nuclear mass is proportional to nuclear volume, right? So mass number, that will be proportional to volume, and for spherical nucleus the volume is equal to 4 by 3 pi r cube. So r is the radius, so we can write this nuclear mass is proportional to r cube. We can write this, right? And if we write this, then you see this mass energy is proportional to A, and A is proportional to R. And you see, okay, then this mass energy is proportional to mass number as well. Okay, so that's why we can write this mass energy is equal to AV into A, which is this is mass number, right? And sorry, this is volume energy, and this AV is the volume coefficient, right? So now let me explain the next term. Here you see surface energy term. This is BS AS into A to the power 1 by 3. Okay, the surface effect of total binding energy is reduced due to nucleons on the surface. Okay, so the on the surface of the nucleus, the nucleons on the surface, so here you see they are influenced by the internal nucleons only. Okay, so here outside the nucleus there is no any other nucleons, right? Because the surface nucleons are not completely surrounded by the other nucleons. So the contraction due to surface energy, which is proportional to the surface area, if you consider it a nucleus to be spherical, that will be 4 pi r square. So that's why we can say that Bs is proportional to r square, right? And r is proportional to a to the power 1 by 3. So instead of r, we're going to put this, right? Because r square will be square of this, right? So that's why we have got this relation. And if you remove this proportionality symbol, then we used to put a equal sign, and this as is surface coefficient, right? So next term is this one, Coulomb energy. The third term, Bc, is the Coulomb electrostatic repulsion between the charged particles, protons. In nucleus, these protons are positively charged, so there will be a repulsion between them. So which is proportional to z into z minus 1. Here z is the number of protons, and it is inversely proportional to this radius r. And combining these two, we can write this, okay? And again, we know this radius is given by r naught a to the power 1 by 3, and k by r naught is replaced by this constant ac, right? So hope you have understood this. Now next term is asymmetry energy. The fourth term, Ba, originates from asymmetry between the number of protons and neutrons in the nucleus. For stable and lighter nuclei, the number of protons almost equal to number of neutrons. As A increases, the number of neutrons exceeds the protons to maintain the stability, okay? And here you see, so this difference difference between number of protons and neutrons, this gives the measure of asymmetry. Here you see, we know A is equal to n plus z, right? So if you see, in case of if the number of neutrons is equal to number of protons, in that case we can write A is equal to twice z, right? If this number, suppose now let me consider that this number of neutrons exceeds z by 1, suppose, then we can write z is equal to n plus 1, right? So then the difference between n and z, how to obtain that? Then you see, if n is 1 more than z, then we, instead of n, we can write z plus 1, right? And z plus z, that's twice z. And here, from here you see a, let me explain it properly. Let me give you an example. Let me explain why this n minus z is equal to a minus twice z. Let me explain it. Suppose, let me take an example. In a nucleus, suppose this number of neutron exceeds z by 1. That means n is equal to, suppose, z plus 1. That means neutron, there is one a new number of neutrons is 1 more than number of protons, suppose. In that case, a plus n plus z, this n can be replaced by z plus 1, right? Z plus 1. So here, from here, a minus twice z, it will be equal to 1. 1 is what? 1 is the difference between, in this case, for this example, n minus z, right? N minus z is equal to 1. So instead of n minus z, we can write this term. So hope you have understood this. So this Ba is proportional to this, and Ba is also proportional to the measure of asymmetry per nucleon. So that's why combining these two, we have got this expression, okay? So hope you have understood this, and this can be replaced by this expression as well, right? So now last term here, pairing energy terms, nuclei with even z and even n, number of protons, number of neutrons, are most stable, and odd z and odd n are least stable. And here you see, I have given the table here showing when this value of this Bp, that is pairing energy, will be positive, negative and 0. okay, in different situations. So these are the applications of semi-empirical mass formula, right? So thank you for watching. See you in the next video. Bye bye.